Hi everybody, this is Tom in the shop. I'd like to welcome all my new subscribers. I'm a little surprised at the reception my earlier videos have gotten, and I appreciate that very much. I'll try to deliver content that you all find interesting and helpful. I should probably change the name of my channel to The Rabbit Hole, because I feel like I'm pretty deep down the rabbit hole on gears and gear making. And one of the interesting things is that the deeper I go, the more I realize I don't know. We talked a little bit about this differential last time, and I was crowing about making a 37 tooth gear, but the fact is it didn't work quite right the first time. And I had to do a little bit of gentle persuasion in the form of a special gear that I made to do it. So that's really kind of cheating what I hope to accomplish. But what it forced me to do was go back and kind of re-examine the math because I clearly had a fundamental misunderstanding about how differentials interact with the universe. So this design that I'm showing now, which I've shown briefly in maybe one other video, this is the differential Rev 2. Basically, I kept the same core of the differential, but I'm hooking it into the system a little differently. Last time I thought in my ill-informed enthusiasm that what I wanted to do was gear these two inputs. And what I was trying to do was develop two rates of rotation here that would add up to the equivalent of 37 tooth gear output on the drum. And that just wasn't going to work the way I wanted it to. So I had to go back and look at the math again. And that led me to this arrangement, which is, this is still the input A, this is output B. So I'm taking the output off this side, which is actually this bevel gear. But instead of these things being ratioed together, I've put a gear between this output B and the drum. And you can just see that countershaft down below that transfers the motion out to this plane. And then there's a gear ratio here that happens to be 28 teeth to 60 teeth, which is the 15:7 ratio that we worked out in the math that's to follow. Here we go. Differential math in less than 5 minutes, I hope. We're going to start with our Hobbing relationship, which is Km over Z, the machine constant divided by the number of teeth that we're trying to make. And Km is the number of turns of the output of the index train that it takes to produce one revolution. And in my case, that's 90. So for me, this relationship looks like 90 over Z. Now, I want to talk about 37. 37 is a prime number, so you can't divide it by anything other than itself and 1 by definition. And so when I try to make a 37 tooth gear, this is what I'm faced with. Now, I can break that down the way we did in the last math lesson by multiplying and dividing by 45. And this can be simplified. That's 60 over 30, that's just 2 to 1. But this one here, I can't really break down in any simple way because 37 can't be divided evenly. And I'm trying to make a 37 tooth gear, and it requires a 37 tooth gear to do that, or a gear that's some multiple of that. I can multiply by 2, for example, and use a 74 tooth gear to make a 37. But at some point, I'm going to run out of good options to do that. So it's either to make this one tooth at a time, which is the old-fashioned way, or let's come up with a machine that will help us make a 37 tooth gear without requiring a 37 tooth gear. Before I start this, I just want to mention that there was a video on YouTube that helped me considerably to get this understanding, and that was a place called technicblockpower.com, or Technic Block Power, and I'll put the link in the description. But it's a guy building these amazing machines out of Lego components, and he did a section on differentials that was very helpful in getting me on the right track. So I'm going to draw the differential the same way he did. And it's a way that should look vaguely familiar if you think about the axle on your car. A and B represent the wheels, and C represents the drive shaft, and in my case, I'm calling that the drum. That's the round thing that carries the bevel gears. And the relationship that defines the behavior of a differential is simply that C averages the two inputs from A and B. So you can say C equals A plus B over 2. Now, just solving this equation for A, you get A equals 2C minus B. And that's an important relationship there, because you can pick A to be whatever gear tooth number you're trying to make and determine C and B such that this is a true relationship. For example, if we set A equal to 37, we can set C equals 19 and B equals 1, and that equals 37. But where the real power of the differential comes in my view, is that you don't have to pick 19. You can pick some other number for C and B. So let's try that. Let's just pick 15 for C, and then minus 7. So I'm picking minus 7 for B. What does the minus mean? It's just opposite. It's counter-rotating to C. So if C is moving 15 rotations in the positive direction or in one direction, B is rotating 7 rotations in the other direction. And if you work that out, remembering that subtracting a minus is the same as adding, you get that equals 37. And that's what I decided to do. So what this means is that this ratio of 15 to minus 7 needs to exist between the output B and the drum C. So this is the ratio C over B, and in my case that equals 15 over minus 7. Now, that's actually a gear ratio. I don't have a 7-tooth gear, sad to say, so I'm going to multiply the numerator and denominator by 4 and end up with 60 over 28, which is the actual gear ratio that I'm using between the output B and the drum C to get 37 revolutions of the input A. So now let's look at this equation again and just divide both sides of that equation by B and produce the ratio A over B equals 2 times the ratio C over B minus 1. Now what we've done by creating ratios here, those can be speed ratios, but they can also be gear ratios. So that can literally be gear ratio, like it is in this case, C over B. I picked 15 and minus 7, and what I end up with there is minus, it's a negative ratio, so A and B have to rotate in opposite directions. But that's okay. That doesn't bother me. I can manage that with my with the rest of my gear train. Now, let's break it down again, or take a different look at the entire train. Remember that Km over Z is our overall ratio for the index train. That's a Z. But Z in this case is A. So I can write this as K mechanical or K machine over A. Now, so this represents our overall ratio for the index train. I can multiply and divide that by B, which is 1, so that I'm allowed to do that. And I'm also going to interchange the denominators here. So this becomes Km over B times B over A. Now B over A is just 1 over this ratio. It's the inverse of this ratio. So we know that. That's determined by the gears, the ratio that we put between B and C. So this represents our overall ratio. Km over B times B over A, which is the inverse of the differential ratio. Now, let's look at what that means for me with my machine. So the overall ratio equals Km over B times B over A. And that equals B over A, the differential ratio, times 90 over 7. Now we need to break that down because I don't have a 7-tooth gear, so I'm going to cross that off and I'm going to say that's 90 over 30 times 30 over 7. Well, I still don't have a 7-tooth gear, so I'm going to multiply both of those by 4, and that becomes 120 over 28. Now 120 is a big gear, so I'm going to cross that off and add another compound, and I'm going to say 120 over 60 times 60 over 28. And that I can simplify. That's just 2 to 1, so that's going to be 60 over 30. So let's write that all down. So our overall ratio equals B over A, which is the differential ratio, times 90 over 30 times 60 over 30 times 60 over 28. So that's the differential ratio. This is the first compound, or can be in any order really, second compound, and this is the third set of compound gears, but that's our gear train. If we have that differential set up to produce the right ratio, 37 over 7, and we have these gears in our gear train, that should equal 90 over 37. And I'll leave that as an exercise to the reader or viewer. But basically, that's how you incorporate a differential into your gear train. And when I push this a little further, I can do this in another episode perhaps. What I found is that almost all of the action takes place right here. You might have to have 1, 2, or 3 compounds in this train between B and C, but you can make any ratio, any of the non-prime ratios as well. So this actually becomes a pretty slick way of doing a differential, or doing a Hobbing index train. The other thing I found out is that Uh, compound 1 and compound 2 don't change when I do this, depending on the choice of B. The only thing that changes is that 28 tooth gear. For odd numbers, it's 28. For even numbers, it's 32. And that's because I picked B equals -7 for odd numbers and -8 for even numbers. So it really simplifies the gear train, and I'll talk a little bit more about that in the next video. Thanks for watching. This is the input A. This is the output B, which is geared to the drum C according to our calculations with a 15:7 ratio. In other words, 7 revolutions of this produces 15 revolutions of the drum. So what I should end up with is a 37:7 ratio here, which I can work with. And what I need to do is, if you divide 37 by 7, you get 5.286 and a bunch of decimal places. But effectively, if I can rotate this gear 5 times this way, this gear should rotate 1 revolution, 5.286 times this way. That gear should rotate 1 revolution in that direction. So I'm going to do that now. There's 1, 2, 3, 4, drum roll, 5. We're still a little bit short. So that needs to go around to about there. So the mark on the A gear is down about there. That's about a little over 2 1/4 turns. And like I said, if you do the ratio of 37:7, it'll be 5.286 and a bunch of decimal places. So I'm going to say that is pretty much exactly what I want.